And let's see how much. I might need to back this up just because. Mr. Tripp, I'm going to back this up so I don't. That means you may have to actually stand and move because I might be going about where you are. Okay, a little bit of reference help here. Keaton, oh, Tripp's standing. Keep going. Keep going.
No, I'll go around.
No, because then I'll be in the way of the thing. 'Cause my
Well,
head's
stand up and kind of stand by that thing. I want to see. I want to see. Okay. That might be about the right angle there. So smaller image today, but there's a reason. Okay. So I've got to be careful about how I phrase things because, well, just because, you know, I kind of like my job. I would hate to be fired this close to retirement. You know, also I would prefer to spend my remaining days outside of jail instead of in, right? So I've got to select my words somewhat carefully. So this is a preamble to this. If I start talking about, you know, how attractive the young ladies in the room are, person my age, that gets a little, oh, who are we kidding? That's a lot cringy, right? But on the other hand, I told the freshman a story, and I think I told you earlier in the fall. That's why we got it out of context. I told the freshman a story about a 13-year-old French girl who a 50-year-old wanted to propose to. That was a little bit creepy. So no, I'm not going to talk about how attractive the young ladies in the room are today. No offense if you think I should. I don't know. But so if I start talking about how attractive the young men in the room are, no, we're not going to do that either. But it kind of needs to be in the story for the story to make sense. So, you know, some years ago I actually had an inanimate object that I treated for this. I had an overhead projector and used that as the thing that was attractive. But in the room right now, I guess you can see I have there was a reason at one time and I never get rid of anything. So I've got Marilyn there, and most people would agree that she's quite attractive. All right, so we'll start from there. So
that's enough out of you.
I didn't say anything.
Once upon a time, there was a handsome prince. Handsome is subjective, right? But there was a handsome prince, and there was a beautiful young maiden, and they were attracted to each other.
I'm gonna tell you what.
The end. Pretty boring story. Let's change the story a little bit here. Once upon a time, there was the handsome prince, the beautiful maiden, but in the kingdom there lived the horrible, evil, nasty, cruel. What are you, Trip? An ogre, a dragon.
We'll go with dragon.
You're a dragon?
That's a better
There
option.
was the horrible, evil, nasty, awful dragon who took the beautiful young maiden to their lair. And you're going to have an awful time at this.
Oh.
There we go.
Oh,
That
want me
would,
to have the
Mr.
sticks?
Mr. Searle won't actually let me bring swords into the room.
Oh,
Go
baby.
figure. On guard. Hey, you know, she is rather cute.
Yeah,
Yeah?
yeah.
Okay. Look over there. Boy, you're bad at this. Okay. So the horrible, evil, nasty dragon, realizing that he is so bad at this, all right, recruits a little help. Recruit some help.
Carson.
Yay!
Okay. So the horrible, evil, nasty dragon recruited,
I can stick.
What is the evil accomplice?
You'd be a goblin.
The horrible
The
evil.
height of it.
What?
Guys.
Guys.
Mean.
Yeah. All right.
I
So
wanna be an elf.
the elf, the
Oh,
evil
okay.
elf.
The evil elf.
Okay. Make room for the evil elf.
Evil elf.
All right. No. Horrible. You. No.
What?
It works better if you sacrifice the elf first.
Ooh, that is true.
Yeah.
Get in
All
there.
right. No offense. So once upon a time, there was a somewhat cute young maiden and a handsome prince. But the horrible evil dragon abducted the young maiden and got the elf to help him defend. You're bad at it too. You need to be ready. All right, that
Can I
wasn't
keep my
fair.
sword?
Go back.
Oh yeah.
All right. Now, so the dragon got some help. Hey, what is that? You're bad. All right. So, hi, dragon. You're worse. All right. So, once upon a time, the horrible evil dragon decided that maybe the mercenary elf wasn't quite as good as they thought they were, so they recruited some more help.
Anna,
Oh.
you're part of this now.
Oh. Okay.
What are you?
Do I get to keep my sword?
Yes.
Who do I wanna be a. I don't know.
Okay.
She's an I don't know.
Come on up here. All right.
Do I come back?
Yes. Well, you wouldn't do a whole lot of good there.
I don't know. Maybe he decided I wasn't worth it anymore.
Once upon a
You're
time,
up for it.
the handsome prince saw a. Well, she's okay. Young maiden over there, and thought about maybe trying to interact with her. All right, and so, but the horrible evil. I forgot all the adjectives now. The bad dragon, bad. Okay. And the mercenary elf and the I don't know. All right. Are defending the
I don't know.
princess, and
Guess
so,
this
but the
side.
handsome prince, what? Oh well, hey, look over there. You're bad. Good grief, these people are awful. I gotta get a better class of new bad people. All right.
Hey, look over there.
Okay.
I came back to life.
Hey.
Got him.
Got him.
Got
Okay.
him.
Now, there's a point to this story, not just the swords, believe it or not. What's the point? I gotta disarm all the evil people. Thank you. Thank you for
Sip
playing
out,
along.
like electrons
All
or
right.
something for the attraction.
You mean there's chemistry involved here? Well, there is chemistry involved in attraction, no doubt. But yeah, if you saw the way I described it, she was gorgeous, right? Irresistible. And then she was,
Less so.
as the evil dragon recruited more help, she became maybe a little less attractive, you know, right? It was gonna be a bigger fight. Now, what the heck does that have to do with anything involved in chemistry? Oh, I don't know, but was it a good story?
Yeah.
Okay. No, there actually was some chemistry involved there. So let's talk about the chemistry. And then I'm gonna go to a PowerPoint and, try to approach this in a somewhat reasonable fashion. But let's see, whiteboard. Okay. New whiteboard. Really? It didn't save any of that physics again? What the heck? It must max out. I wonder. Sorry, babbling to myself. Nucleus. Better nucleus. Overall positive charge. I mean, there's protons, there's neutrons. I don't feel like drawing a whole bunch of them in there. But the nucleus is positive. The electron located around the nucleus on the outside, oh what the heck, don't be too lazy, is negative, right? There is an attraction between the nucleus and the electrons, right? Of course there is. Positives like negatives, negatives like positives. And there's a lot of attraction there. Now, however, okay, if I have a bigger, more complicated atom, second energy level, with an electron living on it, is it attracted to the nucleus? Yes, yes it is. Okay, positives like negatives. Now, Coulomb's law tells me that the further away I get from things, the less the attraction. It's kind of like gravity works too. But there is still definitely an attraction between positives and negatives. But the situation just got a little more complicated. There's a negative between the handsome prince and the fair maiden. No, chemistry. There's a negative between the valence electron and the nucleus. So yes, there is an attraction, but there's also a little bit of repulsion. Okay? Not quite as easy to get to the fair maiden when the awful evil dragon is between there. All right? Now, if the awful evil dragon recruits another helper, is there an attraction now between the valence electrons and the nucleus? Yes, yes there is. Positives attract negatives. But there's gonna be a little bit more repulsion. It's harder to get to the object of your love there because there's a couple of layers of resistance. That makes sense? The more layers I add, I settled for 3, but you know, in chemistry, the more layers I add, the less the attractive force, because there is, well, first of all, I'm farther away, but also there is this repulsive force, right? There's a shield. It is called the shielding effect. Get out your worksheet. And we'll do the ones we started to do yesterday, actually. Let's see, which one? Electronegativity is a good one to leave it on. Okay, so worksheet out. Okay. So the questions that we did like 20 something and 20 some other, and I can do better. Let's do better. Question number 21. We're supposed to use, and 22, we're supposed to use the terms increase or decrease or stay the same. And it's not that we have to use each one once or anything like that. You use whichever one's right. In moving from left to right in a row on the periodic table, so if I pick a row, let's say period 4, That shows up so-so. Oh well. That shows up really so-so. Oh well, I'm gonna live with it. When I'm moving from left to right across period 4, what happens to the electronegativities? We already answered that. They get bigger. They increase as a general rule. There is a place where it dipped here just a teeny little bit, but then it picked back up. Okay, what happens to the shielding effect? The shielding effect is how many layers of bad guys are between the valence electron and the nucleus. So how many layers of bad guys? What's going on there? As I go across, do I add extra layers? No, right? Do I remove layers? No. So when I start here, the valence electrons, they're on level 4, 4s2, and then 3d10. It kind of beefs up the 3d a little bit, but it didn't add another layer. And then 4p. So same levels all the way across, same shield. So 22 is going to remains the same. See, right? In moving from top to bottom, in a column near the right-hand edge, boy, that shows up really badly on it. I'm going to shut off the light and see if it picks it up any better. And it might not. But for a lot of you guys, that's better, right? Bless you. So if I'm going from top to bottom, all right, we already answered this part. What happens to the electronegativities? They decrease, right? 4, 3.16, 2.96, right? What happens to the shielding effect? As I go down, I'm adding another level. So 1 level, 2 levels, 3 levels, 4 levels, 5 levels, 6 levels. I'm adding more and more shield. The shielding effect would go up. The shielding effect goes up, the electronegativity went down. Okay? So 23 is decrease, 24 is increase. In moving from bottom to top in a column near the left edge of the periodic table. So this time, just to be weird, they said bottom to top. Okay? What happened to the electronegativities? As a general rule, they increase. Okay? What happens to the shield?
Goes down.
The shield would decrease because radium would have 6 levels of shield, but barium would have 5, strontium would have 4. That makes sense? So the shielding effect is the, what do we want to say? It's the repulsive force of the interior levels of the electrons on the valence electrons. Fair enough? Okay, let's try something else. So now I want to, what do I want to did? Grab this, plug it into here. Okay, that's interesting. Is it still recording?
Whoa. Nope.
Numbers move in here? It's too small, I can't tell. It's still recording. All right, now, so I don't want that though. I want that. Okay, so as we go through this first section, oh, I forgot to do something. Oh well, we will
Is that in
end.
your room?
Yeah,
Do you hear that?
I did.
I heard that.
When we get through this, we will so now I've got recorded evidence of you thought I was weird.
Though.
Predict the type of bond. When we're done, we're going to predict the type of bond that forms between atoms by calculating electronegativity differences. We will. Nope, what? I hit the wrong thing completely. Let's try that again. There we go. We will compare and contrast characteristics of ionic, covalent, and polar covalent bond. We will interpret the electron C model of metallic bonding. So metals do their own little thing. We will remember that alkali metals are group number 1. Okay. New words for this first section. We've already introduced electronegativity and shielding effect and actually polar covalent bond. You may be familiar with malleable. What's malleable mean? You can shape the metal, you can make foil and stuff. Ductile means you can make wire. And hopefully you're familiar with conductivity. We might need to just brush up on metallic bond. The difference between the electronegativities of two atoms determines the type of bonds that form. That's why we make such a big deal out of it. Atoms form two different types of bonds, or depending on who's counting, 3 or maybe 4. They're ignoring that metallic bond thing. Thank you. Alright, so if we ignore metallic bonds, then we've got nonpolar covalent bonds, polar covalent bonds, and ionic bonds. 3 types, right? The table there is a reminder between ionic and covalent, but again, we're gonna split this a little more fine. So ionic things tend to be crystalline solids at room temperature because their melting points are quite high. Covalent compounds could be a solid or a liquid or a gas, depending on how big the molecule is, but their melting points do tend to be lower. The conductivity in the liquid state, so if, in other words, if you manage to get it melted, will it conduct electricity? Ionic things will. Electricity is the movement of charged particles, so if you got something that's ionic and it's got positive and negative ions, and you melt it, they can move. So yes, it can be a conductor. Covalence? No. Will it dissolve in water? Water likes ionic things, charged particles. So yeah. Will it dissolve in water? Not quite as much. Some things do. Sugar's covalent, it dissolves in water, but not as good as salt. Okay? Conductivity of the aqueous solution. If you dissolve salt in water, will it conduct? Oh yeah. If you dissolve sugar in water, will it conduct? Nope. Okay. Now, there are exceptions to these things, but as a general rule, that's the difference. That's why we've been focusing on, what's the difference in the bonds. Atoms form, what the heck? Well, that took forever. It was displaying something different there and there. The properties of any compound, particularly its physical properties, are related to how equally the electrons are shared. So whether it's big brother with little brother or whether it's 2 even-sized brothers, it makes a difference. But here's the tricky part. And I told you that we had some discussions of where we should draw the boundary line. Electronegativity is a measure of the ability of an atom in a bond to attract electrons. So if you really want electrons, you're probably going to be ionic. If you really don't care that much, you're probably going to be covalent. So if you have a high percent ionic character, your electronegativity is greater. The delta En is greater. That makes sense? But look at this. This is basically a continuous curve. If I said, I need you to come up with a division for a couple of different categories, where would you put it? do you see a natural break in there? You go, well, this is obvious, the division's here.
There's a big jump between HCI and HF.
Ignore, that's an L by the way.
Oh.
Ignore the chemicals. They just gave you particular chemicals are there on the thing. We're not, I see what you're saying, and yes, I agree. Okay, but I'm looking at just the red line. Do you see on just the red line like a natural break where you would say that's where you draw your categories?
No.
I don't. So if you've got to come up with a division, put it where? Now your book said 2. But what's so special about 2? Okay, I said I'm going to use 1.67, which would be about here. Now why 1.67? No particular reason, except that's a nice round number there. Okay, about 50% ionic character. You know, if they didn't give me an obvious one, just pick a round number. We could have put it at 75. Okay, we could have put it at 25. Again, at 50, it's about 1.67. And then the other one I said we're going to use as a split is 0.5. And again, there's no obvious break there, but 0.5 would be at a percent of ionic character of about 10%-ish. But again, nothing magic about it. Just have to have some place to make some categories. So if you're in this chunk here, the bond would be considered non-polar. But if you're here, the bond is considered polar, covalent. And if you are above that, the bond is considered ionic. Now, but notice this. Ionic bonded things we've been calling ionic, have a certain degree of covalence to them, right? It's hard to get something that is completely ionic, okay? It's a continuum. Electronegativity is a periodic property. It varies in a predictable pattern across the period and down a group. We already talked about that on the worksheets. I really hate this table. That's a strong word, but it's somewhat accurate. I extremely dislike this table. Just because they're trying to do something that doesn't work all that well for me. They're trying to make it look three-dimensional. This is like if you were looking down on a cityscape from a drone. Some of the buildings are taller, some of the buildings are less tall. Meh. Okay. But so over here, some of the electronegativities, they're higher, right? And the low ones are here. That's the point they're getting toward. What's wrong with this periodic table? There is something that's just goofy about it. Thank you. Yeah, they only put 17. Why didn't they put group 18? The noble gases tend not to bond. And so if electronegativity is defined as your attraction for bonding electrons, and you don't bond, you got no attraction. So it would be 0. But yet you saw on that one other table, they did assign electronegativities to a couple of them. Now, I'm going to stop here, I think, except for one other thing. It's great. Hopefully you brought your computer. Otherwise, I'm going to chase you to get your computer. because let's get it out of the way. You know that Mr. Searle sent you an email. At least I hope you know that. And so you're supposed to. Wow, my brain isn't braining today. I need you to do the survey. So I'm gonna close my PowerPoint, and I'm going to stop recording.